Okay, so we'll start this afternoon session, also with a talk related to for some part with Suryo model. So the talk is given by Goffredo Circo, and the title is Covariant Momentum Map Thermodynamics.
Thank you. Can you hear me? Yeah. So thanks for the invitation to this very special workshop. Very nice and place to be in this moment, and also very special for the tough organization. So yes, I am also thankful for being here after lunch, which is always a hard task to give a talk after it. So I will say something about something which is related or somehow inspired by Suryo's idea of Lie group thermodynamics. It will be deviating from that, and also that's why I'm interested in having your opinion about these results. And it's motivated, from something which is very far, actually, which is general relativity. So first problem is shit. Okay. Okay. So basically. The whole idea of Suryo Lie group thermodynamics is having a covariant description of statistical mechanics, and this is a covariant typically with respect to the dynamical group of some dynamical system. So in classical mechanics we work, so solution of motions are, covariantly characterized in the phase space of a which is a symplectic manifold, and right there, instead of looking at motions or trajectories, you can have a group theoretic approach and study what symmetry can tell you about this solution without calculating basically them. So going and defining an equilibrium at the level of the phase space of a classical system is very interesting because it allows you to define it in a totally covariant way. Now. Typically in classical mechanics we have symmetries like the one we saw today, Galilean or Poincaré in general relativity. But what I want to explore, in this work, is something very, very radical. So I want to explore something which is more similar to a gauge symmetry with respect to what the dynamical symmetry is for a classical dynamical system, and I want to explore it in an off-shell setting. So not at the level of a symplectic manifold of solutions, if you want, of classical mechanics, but at the level of an extended phase space, what we call an extended phase space. So now when you describe dynamics, you have the space of configurations, and then in a standard Hamiltonian approach, you go to a phase space where you have configurations. So points and momenta conjugated to that, and if you want to be covariant, you extend this to add time. But this is something where you then need to constrain and reduce symplectically to then get to the solution. I want to stay there, so I just want to have a symplectic manifold, and I know that Suryo approach works as soon as you have a symplectic manifold and you act with a symplectomorphism. So in principle, this is a good point, but I don't want to stop there. I also want to generalize this to fields. So I want to use configurations which are not points, like in classical mechanics, but are sections of some bundle. So they are actually fields over some background. And the reason for that, as I was telling you, it was general relativity, in the sense that in general relativity we don't have a notion of statistical mechanics which is fully covariant, because we have an absolute space and an absolute times in principle in statistical mechanics, and we miss an absolute time in general relativity. So is there any way to build something which is not relativistic or general relativistic, so not a relativistic statistical mechanics, but a statistical mechanics which is compatible with the Einstein principle of covariance fully? So we don't have time, we don't have an Hamiltonian. We have an Hamiltonian which is actually vanishing because it's a super Hamiltonian, or what we call Hamiltonian constraint. How can we do that? So one possibility is to look at an inference, a statistical or epistemic approach, so basically on information theory. And the key example is the maximum entropy principle, which is also what we typically use to deduce. I will show you what I mean, to deduce a notion of Gibbs. So in an epistemic way, I mean, I don't need to characterize physically what is the macroscopic observable that I want to build the Gibbs state out of. I want to say, okay, I describe reality in terms of these observables. These are a priori good observables, and I can build by maximum entropy principle a notion of equilibrium with respect to those. Okay. Yeah, the principle least bias statistical distribution, basically. Now, I also want to use deeply the abstractness and generality of geometry, in a sense, which in this talk, as we listen this morning, is encoded in the notion of momentum map. So a group theoretic approach, very intuitive, very abstract. And in this case, it's the symmetry which tells you what are the relevant observables of the system, as I was saying before. So it's not completely free, as I was saying. So an example of momentum map, which was already given by, I will use a lot of notions which were already fortunately given by both Frédéric and Jerry, is the one of energy in classical mechanics. So in classical mechanics, the symmetry we are considering is time translations. Okay, so if you have a configuration space, you have a Lagrangian on the tangent of these, and corresponding Hamiltonian. Yeah, then you reduce to what Suryo calls the manifold of motions, which is basically in one-to-one relation to what I was calling the physical phase space. And inside this space, I can define an energy function basically in terms of the Hamiltonian evaluated on the motions, so on the solutions. We are on shell in this sense, as we say in physics, I don't know. Okay, so the Hamiltonian vector field now is basically the generator of this time translation okay, along the orbit. If you want, basically what you are doing at the level of orbit space, where each point is, so each orbit basically is projected down to a physical phase space, which is each orbit is mapped into a point. So translating here at this level means moving. Actually, I should do something like more interesting would be, this is an orbit at different times. And you see that if I move in terms of initial conditions, basically I shift my initial conditions is like moving on these different slices. So in this sense, a translation symmetry here corresponds to some dynamical information on the orbits. Okay, this is the role that we typically, even without knowing, play with the Hamiltonian. But the nice thing is that this can be generalized to symmetries which are not trivial time translation symmetries, as we saw already today, like Galilean symmetry, the Galilean group, or a Poincaré group. And the task in my case would be to generalize this to the diffeomorphism. So the space-time diffeomorphism group, which is an infinite dimensional degree. Okay. So basically, this was the idea. So maximal entropy principle, epistemic approach, momentum map in terms of geometry, symmetry, which tells you what are the relevant quantities of the dynamics. So Suryo, in a sense, is making a synthesis of these two things, in a way. So it's defining a Gibbs state, which is characterized by macroscopic observables given by the Lie group symmetry, and in terms of a maximum entropy principle. I think I have it here just to give you an idea of what I mean. So in your symplectic manifold, which is now Ham, okay, symplectic phase space, you can define in very general terms what you call a statistical state, which is nothing but a density, basically, a redefinition of the Liouville density. Once you have, you give me like a Borel subset of your symplectic manifold. So you define a statistical state with respect to the standard measure on your symplectic manifold. Now, this has to be related to a probability. Now, what is the? How can I a way to select, if you want, a specific statistical state, which we call Maxwell-Boltzmann, for instance, is to use a maximum entropy principle. So I define a Shannon basically entropy, so the standard entropy in terms of information, with respect to this statistical state, and I constrain the variation to be 0, so the minimization, the maximization of this object, with the constraint that some expected value of some quantity that I define, that maybe the dynamical group told me, to be constant. The result via Lagrange multiplier is this object. Okay, I will give you details at the end, basically, when all the ingredients in my case will be in place. So, so here what you have, well, maybe it was better to give it now. So in this case, I have the momentum map, which was defined as my macroscopic observable, like the energy, for instance. Think of the energy, and which is now a vector in the dual algebra of some group, which I choose. And then I can use, for very special reasons, which will not, preserved in a general covariant case, as a Lagrange multiplier, again a vector which is dually paired, very generally with my momentum map of the algebra for the same group. So my Lagrange multiplier is a vector. So this is a vector temperature, which Fredrik told us. And the two define a co-momentum map, which is basically what is equivariant with respect to the action of the group. So this object is intrinsically covariant because it is based on the equivariance of the co-momentum map. Okay, nothing else. Now, okay, as I was saying, can we extend this formalism to field theories? So we will need to go to a multisymplectic formalism. Can we extend this to groups which are infinite dimensionals, in particular, which are in a sense more related to gauge symmetry than to dynamical symmetry, even if this is not proper gauge diffeomorphism, much more than that. And can we do that off shell? So in a symplectic manifold, which is not the manifold of motions, alla Souriau. You're not interested in this motivation, but that would be nice for finding a common framework theoretically for general relativity and statistical mechanics, which is actually still missing in theoretical physics. Okay. So when I say field is, who's not doing statistical field theory is maybe scared, but I just mean a map. So I just do this parenthesis to say that the field is just a map from some base manifold, which may be spacetime to Rn, or so from some gadget xn to xm. Okay, a field theory is nothing but a variational problem, basically. So characterized by some Lagrangian, which is a function of a position of the base, value of the field on this manifold, and for example, an order jet prolongation. So basically the cotangent, the derivative of this variable, so the equivalent of the velocity, maybe. But there is a multi-velocity because you can define more than first-order velocities if you want at the level of the fields. And the action, as we know, is just an integral of the Lagrangian density over my space. So variational problem means that solution of a field theory, the Euler-Lagrange equation, are just a standard solution that you have in classical mechanics for this object. Now you see that everything you do is differently from classical mechanics is based on densities. You always have to integrate because you never miss the dependence of the base on the fields. Okay. Whereas in classical mechanics, the point would be the field itself. And this will play an important role also. Okay, so if you want just to, since we will talk a lot in terms of sections of a bundle, you can think of this field as realizing, if you want, a notion of graph. So a bundle is basically a set. This is a trivial bundle which is we call a bundle E over some base B. Is basically this connection of information about the point and the value of the function. So you can see this as a graph, a way to represent a graph of this field. This wrong should be G. Okay. So for example, in space-time you have a manifold, and the gravitational field is the metric. The metric will live here, and this, instead of being a curve, would be a manifold itself, which is immersed in this bundle, which is a space-time geometry, which is variational field. Okay, anyway, so this is basically the schematic outline of what I want to do. So I want to introduce the equivalent of a symplectic description for fields, which will be multisymplectic. This is a choice. It can be done in different ways. Multisymplectic formalism is one of these, or the ways to realize this. Then I want to be covariant, space-like covariant, so I want to introduce what I will define as a parametrization, so a further invariance under diffeomorphism of the base manifold. And I want to, at the end, reproduce this Lie group thermodynamics in this weird setting. Okay, so let's see how far we can go with that. So let me introduce first what is a multisymplectic approach for field theory. So you have your manifold, the base I was showing you before. This is an n+1 dimensional manifold we call Xi, mathematical Xi. You have now, differently from classical mechanics, the manifold is not the space of points. So the space of points is this bundle. So the bundle of fields, basically on X. Fields are sections, we say, as I was showing you before in terms of the graph. Section from X to Y. Okay. So the fiber bundle Y, I can use this. So Y is the analog, basically, the configuration bundle now. So this is just formalism, so just to keep up with the formalism. And then I will have a Lagrangian density for my fields, which is defined on the jet prolongation is called, so on the equivalent of the tangent space of the fields into some space of forms. Lagrangian is the density, so this is standard. Now this is an n+1 form defined over the base manifold X, which is n+1 too. So you can introduce log coordinates there. You have a lot of coordinates for your space-time, so for your manifold, base manifolds. You have coordinates for your fields. A is here, the fields has n components, for instance, in this case, is the vector fields with n components. And on the tangent, the equivalent tangent space, you have velocities. You see, you have velocities which are labeled down by two indexes, the components of the fields and the order of the derivatives in the space. So this is the jet bundle and the coordinates on the jet bundle. So the Lagrangian at the end for field theory, just to give you a taste of what it is just something like that, okay, written in coordinates. It's a density, an n+1 form, which is stuck on the base manifold, and is a functional of your fields. So in the same way we pass from a Lagrangian to an Hamiltonian description. In this case, in field theory, we can do the same. So instead of having momenta, we will have multi-momentum, which we define, so conjugate to our field configurations, which are defined via some Lejeune transform. Okay, and in this way, we find the equivalent of the phase space, which is now a multi-phase space for these extra indexes. Okay, this is a cotangent bundle in particular, and then we know that cotangent bundles are by construction symplectic. So this is the initial point where we know we can start thinking about applying groups and getting some analogus of Lie group thermodynamics, but it's not as easy as it seems. Okay, okay. This is just to show you that here we can build the standard characterization of a symplectic manifold. So we have a Poincaré-Cartan and form, n+1 form, and then the n+2 form in this case, which is the symplectic form. So there is an extra n basically. That's it. But this n will play a big role. This is just to give you a mapping between classical mechanics in a relativistic fancy approach. So when you have a configuration space with time included, extended phase space, coordinates, Poincaré-Cartan form, and the same there. This is what I show you. So we are trying to build a parallel. So in order to apply exactly what Suryo does in this new setting. So I want to convince you that it's formally correct. Oh, now the first subtle point. So we want something to be spatial covariant, space-time covariant. So this means that we need to change our field theoretic description. Typically, fields, as we showed, live can be thought as maps, which have one foot on on your manifold X. Okay, so this is my what I was calling Y X, and fields are sections. Okay, so for each X, maybe more. This is my projection, and sections are basically maps which tells me from the point X in big X where I live on this fiber bundle. Okay, so for each fiber at X. So X1. I mean, there is no time to. Each one is a fiber. Imagine each fiber as a tangent bundle. A vector in the tangent bundle, like a velocity, is an object like that. For each point, I tell you what is the value of my velocity in this tangent space. For example, here, I have v1 of x1. Here, I have v2 of x2, and so on. So, in this case, a field, you see, is defined on a fixed background, on a fixed manifold. So, whatever is defined on this background structure, like a metric, is not variational, has not to be varied. So there is an absolute space and time, if you want, in this description, in the standard description of field theory. But we don't want that. We want to dress, basically, this background structure in such a way that also the background will be variational at the end of the day in our theory. And the way to do that, which was developed by Gotay and collaborators. Most of this multisymplectic formula it was developed by Gotay, Eisenberg, Marsden, and Montgomery, and but also many other schools. There is a big school in Spain also. And so a way to do that is basically to define a copy of this space X, if you want, which we call X tilde, where all the gadgets, all the metric quantities which are absolute live. And then define this as a new, like a trivial bundle, where basically diffeomorphism, which are basically change of coordinates, can act so that, I'll show you in details, can act in such a way that can act as proper fields, basically. So here we had fields which were physical fields, the fields of the field theory. Here we have fields which are the diffeomorphisms themselves. But we want these diffeomorphisms to be variational, to be part of our configuration space. It's a bit like when you have a non-relativistic classical mechanic description and you add time to be covariant. You add time as a real variable, and then time becomes variational. You have to variate the. You have a Lagrangian which depends on time. You have to in the Euler Lagrange equation. Yes. Mm-hmm. T. What do you mean T? Okay. So here, this T is played. The role of T in time is played by space-time diffeomorphism. Okay, so slices at the end of the day. So it's not just time which will be variational; it will be all space-time which will become variational. This is the philosophy. I don't know if I will manage to convince you about it, but basically this amounts to add an extra level to this bundle description. So yeah, it's like you have your background, you have your fields. Now you have a background, you have the dynamical background through this diffeomorphism, and the fields on it. So you have something like a dressing of your background in terms of diffeomorphism. This allows you to be fully covariant. Okay, so now your Lagrangian change accordingly. In the same way, when you introduce time as a variational variable, now you have something where also space and the diffeomorphism itself basically become fields with their velocity. And whatever was a fixed object, like a fixed metric, now through the action of the diffeomorphism becomes dynamical, because the diffeomorphisms themselves are fields which are dynamical. So it's kind of a dressing of your absolute notions now become dynamic. Sorry, can you say? They are on x tilde cross x. Yeah, sure, yes. So the all things are on y tilde, which is y cross x tilde cross x. So it's like an extended phase space. Actually, this level is an extended configuration space. But you can define an extended phase space, actually. So this is how the diffeomorphism act on our fields, which are now the physical fields, if you want, and these covariant fields, what are they called? So the diffeomorphism. I don't have a reference for time, so I don't want to go too fast because I'm running a lot. Do you know how long? Shall I finish at half or a bit later? Okay, so I can go slower. Okay, so now consider then this diffeomorphism of the base, okay? And the lift of these diffeomorphisms at the level of the bundle. So this is the way this group acts now on my variable. It acts trivially on the covariant fields because they are already basically defined in terms of diffeomorphisms, and it acts in a standard way, so as a push-forward action on tensor fields on the physical fields. Okay. Yeah. Well, at the level of diffeomorphism, it acts by composition. Okay. So the modified field theory now become diffeomorphism covariant because the Lagrangian is a diffeomorphism equivariant in the sense that if I apply to my fields, so if I get the action of the diffeomorphism, then I get this nice equivariant property. This is fundamental, and to get equivariance at the end of the day, which is the basics of a Suryo approach for our momentum map. So this extended phase space, multi-phase space description is then realized at the level of the cotangent bundle, which is now characterized by this extended n+2 form. So okay, so this basically is the first brick, the first step of our construction. So you have an extended multi-symplectic formalism, which generalized the symplectic framework of Lie group thermodynamics, and is off-shell in the sense that we never say anything about solutions of that. So it's just our phase space, extended phase space. The same thing you would have in thermodynamics when you just consider a collection of points and their momenta conjugated. And now the idea is that we want to use as a group acting on these with the symplectomorphism exactly the group of diffeomorphisms, which are a subgroup of automorphisms of the bundle. This will be a one-dimensional subgroup, so because the action has to be Hamiltonian, as in Suryo. This is it's an important, it's a very important point, because as Frederic was saying, when you act with a subgroup, one-dimensional subgroup, you restrict a lot the number of parameters of. Basically, you have, in this case, it's infinite dimensional. But if you have a finite dimensional group, I mean, you end up with Suryo equilibrium with the temperature, which is not a collection of all the generators, but is a convex, basically. I mean, the generators enters in B in a non-independent way. So this is a fundamental point. And this is normal that, I mean, you expect that equilibrium is not associated to anything else but an Hamiltonian action. So this Hamiltonian action enters also here. We want to be covariant, but we need to be Hamiltonian, which is a kind of a strange point. So yeah, now we have our multisymplectic space-time. Can we build an associate covariant momentum map on that? And this was the work of Gotay et al., which showed that you can consistently define a general covariant, which in this case is general covariant momentum map for the action of diffeomorphism on this multisymplectic phase space. So this is a good thing. Somebody else did it. So you define basically the momentum map as something which now as a map from our multisymplectic phase space to what is now not anymore the dual of the algebra, because now you are carrying this extra structure, so the n form over z tilde. So this is a cross product of the dual of the algebra plus this space of n forms. Notice that you have n forms and not n plus 1 forms, because the Hamiltonian nature of the action, which is codimension 1, it always defines somehow a flux, one parameter subgroup flux in your space. Okay, so it's kind of foliating naturally. So even if you want to be covariant, which means that you cannot foliate in any possible, or if you want foliate, you want to foliate in all possible ways, you need to foliate if you want to use something which is Hamiltonian. And the momentum map is an Hamiltonian object if we associate it to the Hamiltonian action of the group. And so, yes, we have this generalization of the moment map. So now, yes, I think these were the remarks I was doing. So the covariant momentum map provides a right general covariant extension of the Hamiltonian, in a sense. In fact, this is nothing but the super Hamiltonian constraint, basically. And this has this differential part. And this differential part already tells you that you cannot take the average of this object, because somehow the form is already saturated by this. So you cannot take integrals of this. The point is that this object is not a proper functional at this point. So you need to first smear somehow, so integrate this over some hypersurface. Okay. Okay. So if this is superstructure, then it means that and if you can give me the equivalent of Poisson brackets for this superstructure, then I can skip all the rest of the talk, because all the rest is basically, yeah. I mean, if I keep, I mean, confidence with this approach, multisymplectic, then I need before going on, I need to kill this object. I need to kill it. Yeah. I need to kill it by integrating over some foliation. Once I integrate it, then I have a functional, which is my observable again. And also Hélène, Frédéric Hélène was describing how to define an observable by integrating over hypersurface on the phase space, which are actually the graphs of solutions, so in a covariant way. So in this case, we will not do this. We will just integrate this on proper n-dimensional hypersurface, which are given by a canonical approach, so a Cauchy surface. Okay, so the covariant field theoretic formula so requires exactly this further step. Now, this n form on Z should be integrated over hypersurface to get proper functionals. So we need to introduce a foliation, and this again reminds us that we want to be covariant, but still we are dealing with something Hamiltonian. Okay, so we need foliations. So we need to move to a canonical formalism, which is like everything you don't want to use in a covariant approach. So we need a covariant formalism, which means 3+1 decomposition of space and time, but done in such a way that it's still covariant. So done for every possible choice of reference frame, basically. So you introduce a foliation. You introduce a foliation in terms of a slicing mapping. And you want this mapping to be compatible with your one-dimensional Hamiltonian action. So you want that the direction of the foliation coincides with the direction of the Hamiltonian action. So if this was I think I forgot to tell you before, this psi is the realization, basically. No, this is the element of the algebra of the diffeomorphism acting at the level of the bundle. Then you want that this vector, which is the vector labeling my choice of reference frame, if you want, or my foliation, they must coincide. This is called the G-slicing, or G-compatible slicing. It's a way to define a slicing of your manifold in a compatible way with the action of the group, and it's very important. So now our fields are reduced. So we are not taking anymore the whole set of fields, but we will take just the pullback of these fields on slices. Okay, and this will be very important at the level of the definition of our momentum map. So that's what I mean by pullback. So take your fields, pull back down. These fields was defined on the full background, and now will be defined on a slice of it. A slice will be labeled by tau, and this labeling will be of key importance because it's a variational label. So this tau is a dynamical field. Yeah, exactly. So as I was saying before, in the same way we were trying to dress our background in such a way that it was becoming dynamical. In the same way, in this setting, by considering a slicing, we are dressing the slicing. So a diffeomorphism acts on slicing in such a way that our Cauchy surface is somehow a covariant in its choice. So this means that we are choosing all possible Cauchy surfaces, so all possible reference frame by the action of the diffeomorphism. Okay, and this also tells us that now the what we call the configuration space, so the space of fields over which we want to carry the analysis of Lie group thermodynamics, is made of fields, and what is left of those space-time diffeomorphism is now this combination of slices on which I'm acting with the diffeomorphism. Okay, so diffeomorphism reduce space like diffeomorphism and fields, and pullback of fields on slices are our points, if you want. We want to construct now momenta. Yeah. Yeah, fields are a function of so fields, imagine that fields are your points. So phi is a function of x on the slice, and tau will at the same way. But all the functional we are going to build now will be function of both fields. So in particular, when we realize the element of the algebra, this will be depending on tau 2, because it will be realized on it will be attached to some background, and this background is now dynamical. So yeah, so this is the first point when we see. So now we have. So this was our weird momentum map. This is the pairing with the element of the algebra of diffeomorphism. This object was not. We were not able to define a functional. Now we can, because we can pull back on slices via these fields, which are restricted on Cauchy surfaces, and we can then integrate over such slices. Okay, so this object is not anymore the full covariant momentum map for diffeomorphism, but is what is called energy momentum map. In our case, it's a parameterized energy momentum map because we are adding this extra covariance level. So it's not something defined on a fixed sigma, but it's defined on something which is dressed with diffeomorphism. So this is something new we did. This object is equivariant with respect to the coadjoint action of the diffeomorphism group. So it's what we need. It's not yet though what we need, but at least at this level we can show this is a proof. And I just want to make you notice a single detail. In order to get equivariance from something which is not defined on a dynamical background, it's impossible basically. You need to have the action of the group, so the diffeomorphism here, to act at the same time both on the pullback of the fields, so on the fields on which your covariant momentum map is defined, and on the base. So is the action on both things at the same time, which at the end of the day allows you to cancel somehow this redundancy and get the equivariance relation. If this was a fixed background, then this was not possible. So we needed to engineer this, and probably is not the only way to do it, but was a way to do it, and it works. So now at the end of the day, basically, once we go on slices, I forgot to tell you, we are not anymore in a symplectic manifold. We are in a presymplectic manifolds because we are foliating. But we want to quotient to quotient again by the yes, in a sense, this is the kernel of the two form on this space. Okay, so this quotienting of a presymplectic manifold gives us now again a symplectic manifold, which is the space of fields, if we want, on this cotangent bundle. So in a way, we come back to a true symplectic or cotangent bundle description, which is the place we want to be. Now our fields are, you see, are the sections and the embeddings themselves. So this is the cotangent bundle, the structure of the cotangent bundle. Okay. On this object, we can now finally try to implement the Lie group approach. Actually, not. I mean, this is it's a bit long to explain this, but we want to do a further restriction. Why so? Because and this is something which is more addressed to people working on field theory. In fact, we are dealing with the general covariant field theory and the momentum map, the covariant momentum map, covariant momentum map. It's a very beautiful object because it encodes both the gauge symmetry and the initial value, basically problem information. Okay, so inside this potential, this big, huge object, which is the momentum map, there is information about the generator of the dynamics of the fields, but also information about the generator of the gauge symmetry for the fields. So, for example, in gravity, you have that. If you think of gravity in this, in terms of symplectic reduction, at the end of the day, nothing evolves in gravity, but the system is fully constrained by something which is called Hamiltonian constraint, which tells you basically how slices vary from one country surface to the other, and how diffeomorphism act on each surface. So there is a different. One information is about the dynamics, and the other is about gauge. All this is encoded in the same object, which is the covariant momentum map. So we want to go one step more focused on this extra, if you want, submanifold of the cotangent bundle, which is where we can see the structure, when we can disentangle this information about gauge and symmetry. But at the level, I mean, morally, we are working here, in a sense. We want to see what is the actual closed form of this momentum map. So we do that, and basically we write this momentum map. Okay, so now this is our final expression for the momentum map. So this is the momentum map defined now on this space. This is a mistake, sorry. So this is a symplectic space. Is the space where primary constraints of our field theory are satisfied. And now this is a true moment map in the sense that the image is a dual of the algebra. Okay, so we washed away basically the form by integrating, or if you want, mirroring these fields over surfaces. And we are left with something which now we can open once we integrate. And we recognize that in one case we have the Hamiltonian constraint, and the other case we have this is the supermomentum, or the momentum conjugate to the embedding fields. Okay, and this is if you have an idea of what is the relativistic generalization of classical mechanics. In that case, when you add time as a variable and you try to define an Hamiltonian, then you find something like a super Hamiltonian, which is a sum linear in time. I mean, conjugate momentum to time, which is this. Now time is played by the embeddings, and true Hamiltonian of the fields. So this is exactly what you have here. Because this is a very simple, if you want, a very trivial field theory. It's a parametrized field theory. There are theories which are parametric, or if you want, they are covariant inherently. So where you cannot split this information. It will be always stuck here. And gravity is like that. So now we have this nice form, this explicit form. What can we do? Can we build now our Gibbs state with respect to diffeomorphism, the action of the diffeomorphism on this symplectic manifold? Yes. So now we can calculate expected value properly on the space of fields. So this is a generic functional of our fields, embeddings, conjugate momenta, okay, space of fields in R. So this is properly now defined. We can define, this is formal, probably there will be problems if you want to do that. The measure over fields is never well defined. But we can a priori define a statistical state on this multisymplectic manifold. We can define, we can do again the maximum entropy principle. So we calculate the entropy over this state. And I think it was here. Yes, okay. Yes, we calculate the entropy over this state. Now we want, we ask for stationarity of this entropy with a constraint that some macroscopic object, which is the momentum map, in expected value is constant. So this, which now we can calculate properly. And I mean, the standard, if you want, variational problem, allows us to define the basically allows us to define the Gibbs state. But I want to show you a detail which is very important because it's what makes the difference with respect to the standard Lie group thermodynamics. So you see that here, the realization of your algebra element and the momentum map now both depends on these embeddings. They both depend on this diffeomorphism. So basically, and these fields are integrated. So when you calculate the expected value, you cannot separate these two objects. You cannot do that. So in Lie group thermodynamics, basically, this is true. You can confirm this. So the expected value of the co-momentum map is equivalent to the pairing of the element of the algebra and the expected value of the momentum map. In fact, Suryo derives the Gibbs state by starting from the expected value of this object as a vector. This is not true anymore if you have diffeomorphism. So general covariance kind of break this because these two objects basically depends on the same field and you have to integrate them. Okay, so this is very relevant because at the end of the day you have something completely different, but which gives a result which is basically the same. And I'll show you how. So I do the standard variational problem where I wanted just to show that I need to introduce a real Lagrange multipliers now. So they are not the element of the algebra. The element of the algebra is stuck with its dual. I do the standard derivation and I find the standard solution, which is this Gibbs state. Okay. So this Gibbs state now has a beta, which is a real temperature. And the energy is not the momentum map, but is the co-momentum map, which is also, I mean, what we expect, because it's a scalar. So we have a scalar Lagrange multiplier and a scalar object, which is a co-momentum map. So this is different from what Suryo derives, and it's due to the fact that we are dealing with fields. So it's very general. Now, on the other hand, you can think of this as the same object, in a sense, because structurally this dual pairing, I mean, it doesn't care about scalar, which multiplies one of the two, right? So you can define basically this new vector, which is just a scaled one element of the algebra, okay? And this may seem a trick, but in fact is more interesting than that. So what is the meaning of having an element of the algebra which depends on space? It's like having a temperature which depends on space. So you have a temperature which is not isotropic, in a sense. So it's very interesting. So it's a local equilibrium. It's not anymore a global equilibrium. But the presence of this B is what you typically have when you want to pass from a local expression of your thermal equilibrium, okay, which in fact you probably cannot even interpret as a proper equilibrium, in terms of a global time. So this is the way you do. You multiply your exponential family, if you want, by some factor B, and you use a parameterization. You multiply it by normalization, which gives you the proper final state. So the role of this B basically is to scale a local temperature in order to give you a global temperature. So at the end of the day, we find basically the same expression. So if you think of this xb as a multiplication of b times xc. So formally we get the same, and this is the reason why there should be another way to do it without passing through canonical smearing and all this, because if the result is the same, plus this extra interesting information, there should be another way which deals with a different Poisson bracket, basically. Okay, so the last point, I think I may have... Oh, in fact, I was too fast, in fact. So now, the nice thing is that with these formulas, you can do also some thermodynamics, in fact. So you can, once you give me an expression for the momentum map, in particular in terms of the super Hamiltonian and super momenta, then you can write your free energy and derive all the quantities, all the thermodynamic potentials. Now, I mean, the peculiarity again is that here, all the derivatives are not in the space of the algebra. So this is more trivial. I mean, this is really Hamiltonian in a sense. Now the derivatives are in a one-dimensional space of the real parameters, unless, I mean, a posteriori you recognize that the combination again of beta and x recombine to give you again the same solution. So it's easier now. And yeah, so you have an energy, basically a mean energy, or first momentum if you want. And you see this is expressed now nicely in terms of the expected value of the Hamiltonian plus the expected value of this supermomentum. So the information about gauge and fields, or matter fields if you want, that would be in gravity, is nicely disentangled here. The original motivation was, okay, can we do like a space-time thermodynamics out of this? So can we derive dynamical laws starting from these very general formulas? But we didn't manage to do that. So you can define an entropy function at equilibrium, which is in the standard form that we have. So the one Frédéric was discussing, which is now written in terms of a Legendre transform. And again, this is nicely written in terms of these two different information. The information about the diffeomorphism and the information about the actual points, the physical points, which are the fields. Okay, you have the entropy, you have the free energy, you have the heat, if you want the... How can you do actual thermodynamics? So these are potential. Thermodynamic potential is basically thermostatics. Nothing changed. You're just defining quantities which are... So what we would like to do is doing thermodynamics by comparing, by going out of equilibrium and then coming back and comparing these two. And a nice way to do it by using a dissimilarity measure, like a Kullback or KL divergence. Okay. So, and this is nice because in a sense, if you study thermodynamics in terms of in this information theoretic approach, you get for free something like a positivity of the variation of the entropy, second law, second principle of thermodynamics, just in terms of the positivity of this similarity measure, which is very general. So it's also called the Gibbs inequality, for instance. So if you do that, for instance, you compare initial and final state, which are equilibrium, you can, and I give you just two examples of these, which are you can do it in a kind of an isothermal situation, the standard, when you leave beta the same and you change the momentum map. So basically what you're changing is you're changing the reference frame. You're changing the choice of either the two are the same. So if you change the element of the algebra, you're also changing the momentum map because the two are dual, right? So here basically you're taking one flow, and here you're taking a different flow of the different one parameter flow diffeomorphism. So it's like taking two different, I don't know, slicing of space-time, which basically just gauge, in a sense. It's not so physics, but it's interesting to be able to quantify this. So so both are related to an equilibrium, and what you get is that this is greater than 0. If you write in terms of the fundamental potential, you get something like work, which is written in terms of differences of this momentum map at the different temperatures. And you can write this in these terms, like a work, the expected value of work has to be greater than or equal of the difference of the free energy. Okay, these are standard relations that just we want to recover. If you were in a very adiabatic, in small step, basically equilibrium by equilibrium, then you get an equality. so the standard equality. It's also interesting to see how the cocycle plays a role in this thermodynamical potential, but we didn't discuss this. Also because in the infinite dimensional case, there is no way to understand what the cocycle. The isothermal case then can be, I mean, you can, once you do geometry, you can use really Poisson brackets and all Lie brackets in this case. You can notice that this word can be rewritten as the co-momentum map for the Lie brackets. So this nice formula for the work, okay? And also given the equivariance of the co-momentum map, this is the Poisson bracket between the two co-momentum map. So it's nice to have this relation. So the work basically is a Poisson bracket between two different co-momentum maps. It's interesting. And yes, that's what I was saying. So along a coadjoint orbit, as we were expecting, nothing changed because we have this equivariance. And in fact, in this case, we have 0. Okay? So this is compatible with Lie group thermodynamics, also for diffeomorphism. Something changed instead for the adiabatic case. So in the adiabatic transformation, basically, you can recast everything in terms of entropy. This is nice. So now the Gibbs inequality basically directly gives you what is called as a Clausius law or second law of thermodynamics, right? So you have the difference in entropy between. So now what we are doing is taking different B and leaving the co-momentum map the same. So the same slicing of space-time if you want, but different global temperature, reference temperature. You get that if there is a difference in entropy, this is related to and greater than the difference in the expected value of the internal energy, okay? And yes. Yeah, this is standard, so I don't, you look at it and you understand. So this is a Clausian inequality, and again, if you go by equilibrium steps, you get an equality. This is a bit different though with respect to the group thermodynamics, because here, since there is a global information, which was not present in the case of the group, even if you move along coadjoint orbits, this difference is not 0. Okay? Because there is some extra information here. So you move along coadjoint orbits, the entropy doesn't vary in certain respect, but it varies because of the presence of this global parameter. So this is different from what you get. You would get 0 in the Lie group thermodynamics. And yeah, this is everything. Thank you. Yes.
I can speak out loud. Okay. Okay. So I'm wondering if you could have a toy model of your ideas. If we took, instead of phase space, we took configuration space, and then if we took as internal variables, let's say the tangent and cotangent bundle, and we'll be offline in the sense we would not specify a specific equation of motion. Yeah.
So once you have fields and conjugate momenta, you need some extra work in order to get all this extra structural. But essentially what you're doing is this, trying to reproduce a symplectic setting on which then we want to apply the action, the Hamiltonian action of some group. In our case, the peculiarity is also in the fact that the group is a group of diffeomorphisms, which then requires further ingredients to make everything covariant with respect to diffeomorphism. So yeah, if you act with a group of the theory, you take like a Klein-Gordon, I don't know, or a field theory of which you don't care about diffeomorphism in that case, you just want to apply exactly what Suryo did, and you want to select the group in terms of the dynamical group of the field theory, you can do that. And you can just use the field theoretic approach and get exactly the Lie group thermodynamics, I guess. Yeah, exactly. Yeah, in that case, everything will be the same, but the fact that you are dealing with fields. And I guess that because you're dealing with fields, again, you will end up being local in the temperature again, because this is a constructive problem. Once you have densities, once you have field, basically, and you represent the algebra then you have to integrate these fields. So you cannot do the trick of the expected value of the momentum map being the pairing between algebra element and the expected value of the momentum map, which is important for the maximum entropy principle in Suryo approach. So you lose that with fields, but you get basically the same, some similar result. So yeah, morally, basically, this approach can be extended to fields, and a priori can be extended also to infinite dimensional Lie groups. And with the peculiarities of these and all the difficulties are motivated by specific setting like general relativity, but it's very hard to see another application of that. Maybe in information geometry, diffeomorphism will play a role. I don't know. If you have an idea, I don't know if you have intuition about that.
Okay, so I think thank you to Goffredo Chico.